Today we're going to be talking about some postulates and working with diagrams in geometry. Now, postulates, that's kind of a funny word. A postulate is essentially a rule of geometry. And we have several rules of geometry here that we're going to be looking at. Now, it's important to note when we're talking about postulates, they're always going to be numbered for us, and they're going to have names. But what's most important is understanding what the postulate says, because these are our rules. Because the numbering for postulates, the fact that this is 2-1 and this is 2-2 and this is 2-3, etc., that's arbitrary. The author of the book that you're working with can choose to number them and order them pretty much however they want. There's no set rule as to how to number postulates in geometry. So don't necessarily rely on memorizing the postulate number. The names are also a little bit arbitrary because, again, the author has a right to adjust those however he wants. But the statements are universal, so understand what they say. And for deductive reasoning, these are rules that we will often be referring back to. These are basic facts. Now, none of these are difficult concepts, but these are very basic facts that we're going to use quite a bit. The two-point postulate says through any 2 points there is exactly one line. The line-point postulate is the converse. It says a line contains at least 2 points. Now, at first glance, those seem to say exactly the same thing, but in reality, they're opposites. They're converses of each other. So just from a visual standpoint, the first one says through any 2 points there's exactly one line. So from a graphic standpoint, what it's saying is if I have 2 points, we'll call them A and B, then I have a line. So postulate 2-1, the first postulate says if I have 2 points and I have a line, starts us with 2 points and concludes a line. Postulate 2-2 starts us with a line, no points on it, and then concludes that that line must contain at least 2 points. So they are different in that their starting conditions are different. The first postulate there, 2-1, the 2-point postulate starts with 2 points and ends with a line. 2-2, the line-point postulate starts with a line and ends with 2 points. So they're converses. So they're very closely related, but they are not saying the same thing. Both, by the way, I think are very self-evident. The line intersection postulate, if 2 lines intersect, the point of intersection is exactly 1 point. That's just a true statement. We know when 2 lines intersect, they intersect at a point. Unless they're simultaneous lines, but that's kind of we call a degenerate case, something that isn't very interesting because it's so strange to talk about 2 lines and they're actually the same line. A better definition might say if 2 distinct lines intersect. That might be a good word to add in there, but I'm not going to quibble with what the book already has. The 3-point postulate and the plane point postulate are just like the line one, it's just that for a plane this time. It says through any 3 non-collinear points, there's exactly 1 plane. We've already talked about that. The points have to form a triangle to form a plane. That means non-collinear. The plane point postulate says a plane contains at least 3 non-collinear points, just like the previous example. One starts with 3 points, concludes a plane with those 3 points. The other one starts with a plane and concludes the plane with 3 points. So they have the same conclusion point, but different starting points. The line-plane postulate, if 2 points lie in a plane, the line containing that point also lies in the same plane. Again, rather obvious statement. And finally, the plane intersection postulate, if 2 planes intersect, that intersection is a line. Not a segment, but an actual line, because planes are infinite, as are lines. So when 2 planes intersect, they got a great picture of the intersection as a line. If you're not sure about that, look in whatever room you're in. See where 2 walls intersect. You'll see a crease there. That's a line. It's not a point. The planes intersect at a line. Now, some of the homework is going to be identifying which postulate is being illustrated by this. And it's kind of what we just did. So we start with if, and I got two lines intersecting, then there's a point there. Oh, so if you're going to identify which one's being used, we can identify it by name and call it the line intersection postulate. So if you want to call it line intersection for a solution like that, this would be for B, the plane intersection postulate. And the names are pretty descriptive, so it's not a bad idea to kind of learn those names. Beats having to rewrite the entire postulate. Now let's get into diagrams. That's really the more important part of this section. Diagrams are very important to us in geometry because we're always drawing pictures. And so one of the things we have to become good at is drawing diagrams based on a description. And that means we have to read carefully and draw carefully and be careful not to draw special conditions that don't actually exist. For example, if they ask for intersecting lines, don't make them intersect at a right angle unless they tell you they're perpendicular lines or they intersect at a right angle. If you have two planes intersecting, don't assume they're perpendicular planes. Maybe they are, maybe they aren't. So try to avoid sketching special conditions because right angles are special and perpendicular planes are special. Just try to do what's given. A diagram showing line TV intersecting segment PQ at W. All right, so we've got a line TV. So T and V, it's a line. I've got my arrows on both ends, so I've got a line. It's intersecting segment PQ at point W. So I got a segment PQ, and the point of intersection has to be at W. Oh, but it says TW has to equal WV. TW has to equal WV. Didn't quite do that right, but that's okay. Smartboard. I can move it down there. And I can indicate that that must be true. Now, is that exactly in the middle? Did I put it exactly in the middle? No, I didn't. But by putting my little tick marks in there, I can fudge that a little bit. I can cheat a little bit and say, oh, I didn't draw it perfectly, but these marks are indicating to you, the reader, that yes, those are intended to be perfectly congruent. In fact, even if I had it way over here and it's clearly not congruent, the tick marks validate what's being said in that. It's not a perfect picture, but the marks are helping me out. And so that would be a good drawing. Not a perfect drawing, but a good enough drawing. Which of the following statements cannot be assumed from the diagram? Can I assume that A, B, and F are collinear? A, B, and F. Let's find those points here. A is here, B is here, F is here. Can I assume those points are collinear? Yes, I can. Why? Because they're actually drawn on the same line. That's a yes. That may be assumed. E, B, and D are collinear. Well, let's locate them. E, B, and D. Well, it kind of looks like maybe I could get all three of those points in the same line. But since they aren't actually drawn on the same line, I cannot assume they are collinear. So that's a no. Cannot assume that. Line AB is perpendicular to plane S. Okay, line AB, whoops, my highlighter. Line AB is perpendicular to plane S, the horizontal plane. Well, look what I got right there. I got a little right angle indicator. So yeah, I can go ahead and make that conclusion. The right angle indicator tells me that. If I didn't have that indicator, I could not make that conclusion, but that little right angle mark says yes, that line is perpendicular to that plane. Line CD is perpendicular to plane T. Let's take a look. Line CD, plane T. Ooh, I don't know that to be true. There's nothing to indicate that that is a right angle. So no, cannot make that conclusion. And finally, AF intersects BC at point B. So AF intersects BC at point B. Yes, that's drawn, so that is a valid conclusion. So again, reading diagrams and being able to interpret them accurately without jumping to conclusions is important. If the given information states that PW and QW are congruent, how could you indicate that in the diagram? Segment PW and segment QW. Sorry, I don't have that particular diagram here. But if I wanted to indicate that PW and QW are congruent, how could I do that? We already talked about that. How do we indicate congruent segments? The tick marks. Those two are congruent. If there are multiple things to be indicated congruent, sometimes we'll use a double tick mark or a triple one to show segments are congruent. That's how we show segments are congruent. A pair of supplementary angles in a diagram. Well, if we look back to this diagram, what would be a pair of angles that are supplementary? Supplementary means we have to know they add up to 180. So not having a whole lot of choices here, I could say ABC and CBF, because they form a straight line, are supplementary angles. And I can assume that because we can assume that a line that appears to be straight and is drawn straight is straight. So angle ABC and angle CBF. For some reason, we do not have this particular diagram, but I will see if it's in our student journal here real quick. So bear with for just a second. Or if we have to get this out of the actual book. So we're in section 2.3. There we are. I do not have that actual diagram with me, so we're just going to have to kind of go with this for now, but we'll talk about this stuff more in class. I'll cut the lecture short, give you a little more time to be working on work and stuff like that. So we'll go ahead and cut these last couple examples, but all set for you in class for tomorrow, and we'll see you in class.